So, last time we looked at normal forms and we also looked at actually the notion of Herbrand algebra. So, let us just quickly go through this. So, we have this usual quantifier movement and you can move quantifiers in such a way that you can construct what are known as Prenext normal forms, which are essentially mean that up to logical equivalence you can transform any first order logic formula into a form in which there is a sequence of quantifiers followed by a body which is quantifier free. Yeah. Okay. So, this is important, and then we had the Prenext normal form theorem, which essentially states that you can convert any formula phi into a logically equivalent formula psi in Prenext normal form. And of course, since the body is quantifier free, it can be transformed into a conjunctive normal form, essentially the way in which propositions can be transformed into conjunctive normal forms. Right. Then we looked at the notion of a Herbrand algebra, where I said that basically we are looking for models within the language of terms itself. So, that is why, so essentially the term algebra itself is your carrier set or your domain of discourse, and the functions automatically give you new terms from this set according to their rarity and so on. And the only thing that is left unspecified is really the meaning of the predicate symbols, the atomic predicate symbols. And so, the notion of an interpretation therefore essentially depends upon what kinds of so firstly, so the notion of an interpretation in this case then works out to just a substitution of the appropriate terms by terms for the variables, and the notion of a model essentially reduces to that of finding an appropriate valuation or an appropriate substitution. Actually, that is enough since we have got only a finite number of atomic predicate symbols in any formula or any finite set of formulae. Though of course, if the set of formulae is infinite, you might have an infinite collection of atomic formulae also. Okay. So, we had the notion of a ground term. So, this requires that there should be at least one constant in the signature, and if there is not a constant in the signature, what we do is we just expand the signature to include a constant symbol. And what we essentially showed was that for literals, so ground literals, so that means these lambda i's are essentially atomic formulae or negations of atomic formulae in which there are no variables, and the parameters of the formulae are ground terms of the Herbrand algebra. Yeah, right, ground terms. So, therefore, there are no variables at all, they are completely variable free. So, this first of all these are quantifier free, and then they are ground. So, they are completely variable free also. Yeah. So, we had this theorem on ground quantifiers, which clearly gives us a syntactic characterization. That's the important thing. It gives us a syntactic characterization of logical validity of and of it gives us a syntactic characterization of unsatisfiability essentially. Here in this case for an and of finite set of literals, and here it gives you a syntactic characterization of validity for an OR of a finite set of literals. Yeah. Okay. Right. So, next today we will do what is known as Skalemization, which essentially comes from the name of Thoraf Skolem, who came up with this whole thing, and we will see its relationship to Herbrand algebras. Yeah. So, the first thing we have here is the Skolem normal form theorem. says supposing phi is some it's some Prenext formula which is of this form. That means, there is a sequence of universal quantifiers. So, now we are not, our quantifiers are not any general quantifier q. So, there is a specific form in which we are looking at these formulae. So, there is a sequence of universal quantifiers. So, this is like for all x 1, for all x 2 dot 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 for all x n, followed by a let us say a single existential quantifier. So, there exists y, and this psi is of course quantifier free, and it can contain these variables x 1 to x n and y as free variables, and of course, we will assume that these are all distinct variables. So, and we will assume that psi is quantifier free. So, this is essentially a Prenext form in which there is a sequence of universal quantifiers followed by an existential quantifier. Then what we will do is we will expand, then what we can do is we can expand the signature with a new function symbol g, which is of arity n, where this n is the same as this n x 1 to x n. Okay. So, you can expand the signature to sigma to sigma g, such that then, and what you can do now is, instead of you can replace all free occurrences of y in the quantifier free formula of psi by g of x 1 to x n, right. So, take this formula for all x, for all x 1, for all x 2, for all x n, this formula phi prime for any model of this formula is also a model of phi, because if phi anyway is a sigma formula, therefore, it is automatically a sigma g formula also. So, it is so that way there is the fact that you have expanded the signature keeps phi also in sigma g. So, there is no problem. So, and every model of phi can be expanded to a model of phi prime. Of course, phi prime is not in this, phi prime is a sigma g formula, it is not a sigma formula because of the addition of the extra function symbol g. So, what the Skolem normal form theorem essentially says that is that you can always, so every model of this phi prime where the existentially quantified variable y is replaced by a function of all the universally quantified variables that precede that existential quantifier. So, that is the signature, that is the connection. So, so it can be replaced by a g of x 1 to x n, where x 1 to x n are all the universally quantified variables preceding this existential quantifier of y, right. So, you can, right. So, this is what, so this is essentially like what we are saying is the analogy is readily there, for example, in the theory of groups, right. I mean, so if you take a group axiom like for every x in the group, there is a right inverse, Here what you are saying is that you are formalizing that there is a right inverse by a function which is essentially the inverse operation. Yeah. But you have to remember one thing, in sigma g these two formulae phi prime and phi are not logically equivalent. And so, what we are doing now is we are getting away from logical equivalence and we are getting into the domain of pure model theory. So, the existence of a model, so all that we are saying is that if there is a model for phi prime, then the same model can also be used for phi to satisfy phi, but phi prime is not logically equivalent to phi, right. Simply because it it is quite possible. Let us go back to the example of that group and group inverse. It is possible perhaps for me to construct something very much like a group, except that it does not have unique right inverses, let us say. I mean, or an element might have more than one inverse, let us say, right. So, in which case that inverse operation is no longer a function, right, but all that you are saying is that every group is a model of that axiom, right, and not necessarily the other way. And but you are saying something more important. You are saying that, I mean, my search for models might go anywhere, but I just have the guarantee therefore that if this does possess a model, then that also possesses a model, right, and in fact the same model can be used. So, and you take any model of phi, you can expand it to a model of phi prime, basically. That is, so I can always find a system with unique inverses which will be a model of phi prime, right. Okay. So, this theorem is not actually I mean, it is not very hard to prove, okay, but first of all you should note that g of x1 to xn for y is admissible in psi, and the other thing you have to note is that this phi prime logically implies phi. As I said, they are not equivalent, but it logically implies phi. So, which means that for every sigma g model of phi prime, phi also holds, right. Now, if you were to take this take the converse, the second part, every model of phi can be expanded to a model of phi prime, then essentially you consider some model of phi and there exists at least one element. So, what we are essentially saying is you take this formula phi, there exists at least one element A for every n tuple A1 to An, such that phi in which A1 to An replace x1 to xn and A replaces y would be true, right. So, then you define this, you just choose an arbitrary element. So, in a certain sense you are using the axiom of choice in if you were to think of it as part of set theory, and you just define a function. So, you choose an arbitrary element A that satisfies this predicate psi for each A1 to An, and you choose one arbitrary element for each n tuple and define this function g, right. And then it is clear that you have expanded the signature by this, and it is clear that truth value also holds. So, essentially therefore, you take any model of phi prime, that is a model of phi. So, now that the fact that there exists at least one is clear from the function g. Remember that in our signature all our functions are total. So, there is no partial definedness anywhere. So, the g actually g is a total function. So, for every n tuple A1 to An there is an element A which will satisfy psi, for example. And also we have shown that basically you can expand the signature from and create a model for phi prime using this function g, right. But what this means, and the corollaries are actually more important, is that there exists a model of phi if and only if there exists a model of phi prime, right. And conversely, phi is unsatisfiable if and only if phi prime is unsatisfiable, right. So, that is, so what it means now is that we are going to work with these phi primes, right. So, remember phi prime is not logically equivalent to phi, yeah. So, okay. So, so we come to the notion of a Skolem normal form in which we do not preserve logical equivalence, but we preserve satisfiability. So, the some books which use the term equisatisfiable, right. So, that is like saying that is essentially this part 2 of this corollary 2, which says that phi is satisfiable if and only if phi prime is satisfiable, right. Okay, so they are said to. So here is an equivalence relation, which is well finer than logical equivalence, right. So if they were logically equivalent, they would satisfy exactly the same models, right. Whereas what we are saying now is that they are not logically equivalent, but the quest for models is such that you can replace the quest for models for one formula by the quest for models for the other formula, right. Okay. So, what is known as a Skolem normal form. So, what this also means is that you can get rid of these existential quantifiers through a Skolem normal form. If you get rid of these existential quantifiers, then you can define equisatisfiable formulae. And so, in a Skolem normal form, we essentially consider only universally closed formulae, right. So, the set of Skolem normal forms is the set of universal closures of quantifier free formulae. So, you take any quantifier free formula essentially using propositional connectives and just close it on all the variables, universally close it on all the variables, and that is a Skolem normal form. Yeah. So, and of course, the quantifier free form body can be written in conjunctive normal form. So, you have a Skolem conjunctive normal form, right. Okay. So, here is a simple theorem for every sentence of first order logic. There is an algorithm which I am going to call a function SCO to construct a closed universal formula psi in Skolem conjunctive normal form, such that this formula phi has a model if and only if psi has a model. And the algorithm is actually trivial. You just take the formula phi, transform it to Prenext conjunctive normal form, and what you do? You create what are known as Skolem functions. So, that function g that we created in terms of all the universal quantifiers preceding it is called a Skolem function. Okay. So, what do? You take a formula in Prenext conjunctive normal form, reading from left to right, read it from left to right, take the first existential quantifier and Skolemize it. When you Skolemize it, what you are doing? What you are doing is you are adding an extra new function symbol and of arity equal to the arity of the preceding sequence of universal quantifiers. And when you do that, and when you replace all occurrences of that existentially quantified variable in the body by the corresponding function, then what you get is you have a longer sequence of universal quantifiers, and then you probably have another existential quantifier, in which case you Skolemize it in the same way. So, if you started, if the first existential quantifier occurred in so essentially what you are saying is, if I have for all x1 to xm1 and there exists y1, then I have for all well, I should probably 1 m1 x2 1 dot 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 x2 m2 there exists y2 and so on and so forth. My corresponding Skolem functions will essentially be firstly a Skolem function g1 of sort s raised to m1 arrow s, okay. And this formula phi by this replacement. So, there is some body here, yeah, some body psi here. It becomes a phi prime, which looks like for all x11 dot 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 x1 m1 for all x2 1 dot 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 x2 m2 there exists y2 whatever and the psi is replaced by psi prime, where psi prime is just equal to psi in which g1 of x11 to x1m1 replaces y1. Yeah. Once you have done this, you get this phi prime, and essentially what you are going to do now is you are going to Skolemize this y2 by a function g2 which has a sort s m1 plus m2 arrow s, okay, and you are going to get a formula phi double prime which is essentially will essentially have this up to for all x2 m2 and then blah blah blah, and then a psi double prime, where the psi double prime is essentially psi prime in which all free occurrences of y2 are replaced by g2 applied to these m1 plus m2 arguments, right. So, you can sequentially from left to right Skolemize each existential variable one by one, and you can actually create the final formula, let us say psi, yeah, which will consist only of universal quantifiers and then a body which is in conjunctive normal form. Right. So, this process of constructing these functions is called Skalemization. Yeah. Right. So, okay, I am going to skip this. Yeah. Okay. Now, what happens? We look at our Herbrand algebras, okay, and we look at the notion of Skalemization. So, what this means is that up to the existence. So, the problem of satisfiability therefore, can be restricted to just universally closed predicates in Skolem normal form, and if you need it Skolem conjunctive normal form. Yeah, right. So, now what we will do is let us look at an interesting theorem by Herbrand. So, you take any signature and you take any formula phi. I can talk about the ground instances of phi. Yeah. By the ground instances of phi, which I am going to call it g of phi, where this g is a Gothic g. Yeah. Okay. So, essentially what we are saying is you take all the free variables in psi. Phi is of course of the form universal closure of, oh I am sorry, there is some okay, there is a mistake in, I should not have used psi here, this should be chi. Yeah, this should be chi here, and this should be free variables of chi, right. So, essentially what we are saying is you replace all free occurrences of the free variables in psi, let us say x1 to xn, by terms t1 to tn respectively, such that t1 to tn do not contain any variables. So, they are what are known as the ground terms, right. So, what you essentially are getting by ground instances is a collection of formulae that essentially look like propositions, right. Basically, they are like propositions. Since our predicates are essentially parameterized propositions, you replace all the parameters by appropriate terms which do not contain any variables. So, they become essentially like propositions, yeah, of indexed by the actual parameters. Yeah, right. So, now for each universally closed formula which is existential quantifier free, Okay. For each universally closed formula which is existential quantifier free, you find the ground instances for all over all the terms of the algebra, right. And for any set of formulae of this kind, well, you just take the union of all the ground instances, right. So, this is, so we will call this, we will call this G of phi the ground instances of phi. Yeah. So, now we have an important theorem which says that let sigma be any signature, and actually you want sigma to contain a constant at least, because otherwise there are no ground terms. If there is no there are only terms with variables in them, then there are no ground terms. So, sigma should have a constant, but if necessary we just expand this signature sigma arbitrarily to include a constant, yeah, include at least one constant. Let phi be some set of formulae which do not have existential quantifiers anywhere in them. They are universally closed on a, each formula in capital phi is a universally closed formula over a quantifier free body. Yeah. Then the following statements are equivalent. Phi has a model, phi has a Herbrand model. The ground instances of phi has a model and the ground instances of phi has a Herbrand model. Okay. It's so the significance of considering only Skolem normal forms is that normally in any first order, in any theory that you are talking about, the axioms of the theory are essentially universally closed formulae in a Skolem normal form. So, you look at your group axioms, you look at axioms for number theory, whatever, all of them will be axioms of the form some universally quantified a universal closure over essentially all the free variables of the of a body which is quantifier free. Yeah. Okay. And now there is given essentially a set of axioms, you want to know whether this set of axioms has a model, and for that what Herbrand's theorem essentially says is twofold. Firstly, given a set of axioms, you do not need to look at the space of all possible mathematical theories to find it. If there is a model anywhere in that space of mathematical theories, then there is a Herbrand model also, right. Secondly, what it says is that I do not need to look at satisfaction from a Hilbert system proof theoretic point of view and prove everything. All I need to look at are the ground instances, and in fact the ground instances in the Herbrand model, that is it. So, I can restrict my search to essentially just ground instances of the formulae within a, by just looking at the terms. So, it is a completely syntactic quest which does not have to look at any abstract algebras at all, right. Okay. So, this is an important theorem. So, let us try it, and what we are essentially saying is that all these statements are equivalent, which means essentially your quest for models comes down to just checking whether G of phi has a Herbrand model, right. And so, we have to prove all these. So, there are 4 statements which are meant to be equivalent, but what happens is you can see that if phi has a Herbrand model, then it definitely has a model, right. So, that is okay. So, similarly, if G of phi has a Herbrand model, then G of phi definitely has a model, right. So, 2 implications are out of these are obvious. Okay. If phi has a model and every formula in phi is in Skolem normal form with a universal closure over all the free variables of the body of the formula, then if phi has a model, then clearly G of phi has a model. All the ground instances of phi have a model, because it is a universally closed formula. So, for all possible substitutions of terms for the variables of the body, it should be true. And so, therefore, 1 implies 3, and that is also trivial. By the same sort of argument, 2 implies 4, right. So, finally, what it means is that you have got this statement 2 implies statement 1, statement 2 implies statement 4, statement 1 implies statement 3, statement 4 implies statement 3. So, in order to prove that all 4 statements are equivalent, we just need to prove that statement 3 implies statement 2, and then you will get 2 cyclic triangles, so that you can traverse, so that your implications can traverse all the way. Yeah, right. So, that greatly simplifies our problem. So, so here is a claim that statement 3 does imply statement 2. So, what are we going to do now? Statement 3 essentially says that the ground instances of phi has a model, and we are going to prove that therefore, phi has a Herbrand model. So, given a model of the ground instances of phi, we have to construct essentially a Herbrand interpretation to show which will be a model of phi. Yeah, right. So, what do we do? So, assume that the ground instances of phi have a model. Let us say it is some algebra A. Notice that it is in brown, it is brown in color, right. I mean, I cannot assume anything arbitrary, right. I mean, I have to assume something totally arbitrary. This A may not be a Herbrand model, it could be a Herbrand model also, but it may not be a Herbrand model, because we do not know for a fact that a Herbrand model exists. All we know is that a model exists. So, this A is some structure with the same signature, and the signature of course contains at least one constant. Okay. So, we define a Herbrand interpretation H as follows. So, for every, of course, in the case of a Herbrand algebra, the terms anyway their interpretations are already defined. It is only the predicates, the atomic predicates whose interpretations need to be defined as relations on the terms, right. So, for every ground tuple T 1 to T n, okay, by the way T 1 to T n has to be ground, which I have not, yeah, I have specified it is ground. Yeah. So, for every atomic predicate symbol P that occurs anywhere in phi, in the formulae of phi, I look at what, I mean, if A is a model for all formulae of phi, then it is true for all these tuples also, it is true for some tuples, right. So, I take all those n tuples and I include them in my interpretation of P h. P h is the corresponding relation on the Herbrand algebra, right. Right. So, in particular, if P is an atomic proposition, of course, then by atomic proposition I mean that P is a zeroary relation, right. So, which means that it only has a truth value true or false, then I assign P the same truth value as it gets assigned in A, right. And with this construction exactly the same atomic formulae are valid in A and H, right. And therefore, you can just use structural induction to show that H under this interpretation of atomic formulae is a model of G of phi, and therefore, also a model of this statement too. So, phi has a model, right. So, this is an important theorem, and in fact, this is the theorem which actually makes says things like logic programming possible. It also restricts all our attention to, I mean, it focuses our attention from arbitrary abstract mathematical structures, so that we can look at more concrete terms, just terms constructed in the Herbrand algebra. So, we need to focus exclusively on just the formation of terms in this language of first order logic. Yeah, right. So, let us look at, so what happens now? So, we need to restrict ourselves only to Herbrand algebras, and we need to restrict ourselves only to terms, and in fact that is what mathematicians have been doing for centuries now. They constructed some algebraic system, there is some mathematical system, and they looked at all the terms of the mathematical system, that is it. And in that sense they were focusing only on the Herbrand algebra, right, and they were coming up with essentially their theorems based on the patterns of these. So, an algebraic theory would essentially be based on the patterns of the terms. So, if you look at arbitrary arbitrary structures like so if you have done some number theory, for example, it is clear that if you were to take say the natural numbers modulo some prime number p, yeah. So, you essentially take n quotiented by p, where you have a congruence modulo p, right. In a certain sense, so what a standard number theoretic theorem would say that, okay, by the way, this you take the integers under addition form only a monoid, yeah. But you take the integers modulo p where p is a prime, then that forms a group under addition. If you do not believe me, go home and work it out, yeah. And in fact, what you can do is, it is possible to get an isomorphic structure of ZP, ZP is integers modulo p. It is possible to get an isomorphic structure for ZP by just choosing a group by just choosing a single symbol A, okay, and putting in the operations of, let us say, concatenation, right, and essentially you are able to generate all the elements from essentially from 0 to p minus 1 as this putative multiplication operation, which is just concatenation of this element A with itself. The 0th concatenation of this will give you the essentially an empty string, if you like, okay, and that empty string is the identity element of the group, and of course, it will circle in multiples of p, right, it will circle through, but till you come to p you have generated p elements. So, essentially a raised to I, where a is just some arbitrary symbol, a raised to I denotes the equivalence class I, where I is lies in the range 0 to p minus 1, right. So, so the group ZP can be completely simulated by just using a symbol A and concatenating it to itself. So, that this is a transformation of group operations from ZP to this essentially strings of symbols, right, where the moment you, so A raised to p plus 1 in this concatenation would give you A again. I mean that is what will happen. So, that is an equation of the group which will, and essentially for every I A p minus I is the inverse, right. A p minus I of course is equal to A raised to minus I also, I mean in the same thing. So, what it means is to play around with ZP, I do not need to consider abstract number theoretical notions, I just need to consider a single symbol and that its concatenations with itself up to p, so that it cyclically generates the group, right. That is very much like just looking at Herbrand interpretations, right. So, you have a more concrete thing. If you look at numbers as being abstract, you have a more concrete thing in terms of strings, which will give you exactly the same kinds of properties. Yeah. So, all the properties of ZP will be captured by this string concatenation by this group of on a single symbol A, right. So, okay. Then let us look at what is the notion of a Herbrand interpretation. So, what we are saying is, so for every for every formula which has a model, there is a Herbrand model, and of course, in the case of a Herbrand model, basically you have to find a Herbrand interpretation. A Herbrand interpretation means that you just basically have to assign to all the predicate symbols appropriate relations in the set of ground terms, right. So, a Herbrand interpretation is essentially this tree. So, assume you got all you got your atomic predicates symbols P naught and you got your ground terms. You assume any enumeration of the ground terms, okay, and you got your atomic predicate symbols small p's, they are all small p's. Now, for each small p and a of an appropriate arity and a collection of ground terms, I still have your T naught sigma is countably infinite. You have in your sigma a finite collection of atomic predicates p, q, etc., and I can take all the ground atomic predicates, which are essentially like atomic propositions, right, with indexed by the tuple of ground terms, right. That set of all ground atomic formulae is still countably infinite, right, and therefore capable of an enumeration. So, I call that enumeration capital P naught. So, by the way, this capital P naught means that it is some small p with a tuple of appropriate tuple of ground terms in violet. Yeah. Okay. So, I have this, if I construct this collection is still going to be countably infinite, and therefore, it has some enumeration, right. So, I take this enumeration, and if I construct this tree such that for each of these p naughts, the left edge is labeled p naught and the right edge is labeled not p naught, and I go through this enumeration, then I get essentially an infinite tree, okay, such that each infinite path in this tree corresponds to a certain assignment of relations to the atomic predicates in my signature sigma, right. So, all I am saying is, supposing your the first element in your enumeration is essentially some atomic predicate small p, which is with some n tuple of ground terms, right. Supposing this is capital P naught. Yeah. So, what you are essentially saying in your interpretation is that this tuple T 1 to T n belongs to the Herbrand interpretation of this small p if you take the if you take this left edge, okay, and it does not belong to p h if you take this right edge, right. You have got all terms, all n tuples of terms. So, essentially, and you got an enumeration of all these big P naught, P 1, you essentially got an enumeration of all possible ground terms applied to all possible atomic propositions in your signature. So, any path in this tree, you isolate a single path in this tree, that single path corresponds to essentially a full interpretation of all the atomic predicate symbols, right, which is what you want, right. Okay, so this is, I am going to call this the Herbran tree of interpretations. It is a non-standard name. I need some way of referring to this tree, so I have given it that name. Yeah. So, this tree encompasses all possible interpretations of the atomic predicate symbols P. Yeah. Okay. Why do we require this tree? I mean, it's one thing, of course, it's a so the tree is a binary tree, but it's infinite. So, one thing is important that's important is that it's finitely branching, right. That's at any level there will be only a finite number of nodes. Yeah. Okay. So, it actually brings us to compactness, right. So, you take, so what I am, so here is a lemma which we are going to prove, because compact, now we have shown by other means compactness of propositional logic. Ground terms applied to atomic predicate symbols is the closest we are coming to propositional logic. So, in a certain sense they are like propositions. However, we need to prove a compactness theorem essentially to show that there is a compactness also holds for quantified formulae. Yeah. So, this lemma is the first step towards that, and this lemma is going to use that Herbran tree of interpretations. Yeah. Okay. So, let theta be a finite or infinite set of ground quantifier free formulae. Remember that when we are talking about proof theory, we are talking about our gamma being finite, right, whereas now I am saying theta could be infinite too, it does not matter. So, essentially the compactness theorem for closed quantifier free formulae, closed quantifier free formulae are basically ground quantifier free formulae. Then this set of finite or infinite ground quantifier free formulae has a model if and only if every finite subset of theta has a model, right. Okay. So, we are going to prove this, and we are going to use the Herbran tree of interpretations. One is that it is an if and only if, but if theta has a model, then every finite subset of theta is also a model. And in particular, we need, by Herbran's theorem, we need to concentrate only on the Herbran models. Yeah. So, it is enough to consider only the Herbran tree of interpretations. Okay. So, what we will do is we will prove this, we will assume that every finite subset of theta has a model, has a Herbran model, but theta itself may not have a model, supposing, and then we will prove that there is a contradiction, right. So, what do we do? So, now it is enough to concentrate on Herbran models. So, this is equivalent to saying assume every finite subset of theta has a Herbran model, but theta itself does not have a Herbran model. Yeah. Okay. So, if theta does not have a Herbran model, that means none of the paths, none of the infinite paths in this tree is a model of theta. Take any arbitrary path, if it is not a model of theta, then there is at least one formula in theta which is contradicted at some finite point in that path. Yeah. If that, so you take any, so what you are saying is if theta does not have a model anywhere here, then no path is a model of theta. So, each path corresponds to a Herbran interpretation, and therefore, you are saying that there are no paths which will completely, which basically are assignments of this kind which do not satisfy, which make at least one formula in theta false. So, every path in this tree makes at least one formula of theta false, and it makes at least one formula of theta false means that there is a specific point at which that formula is known to be false. That specific point basically corresponds to a point when the assignments to all the relevant assignments to the when you have encountered all the ground terms that appear in that formula, and when you have encountered all the atomic predicate symbols attached to those ground terms also have appeared in that formula, at some point you know that it is false, right. There has to be a, if it is falsified, then there has to be a finite point at which it gets falsified in each path. Okay. So, let me call that finite point essentially as a level, right. So, you take, so here is the crucial sentence, hence for every path pi there exists a formula chi pi belonging to theta such that the Herbrand algebra with this valuation v pi, each path corresponds to a valuation with this valuation v pi does not satisfy chi pi, which means chi pi becomes false. And this, so this point, let me call this level, there is a level in the tree, right, starting with the root node being at level 0 and so on and so forth. So, let me call this point L chi pi, the point where it is first known that chi pi becomes false along that path, right. So, now we have this, now of course, the tree is infinite and therefore, has an infinite number of paths. Now, I choose all these chi pi's, okay, and I construct the set of these formulae. My claim is that this set is finite. At the moment, all I know is that in every path there is a point at which some formula becomes false, some formula in theta becomes false. I identify the first occurrence of that point and call that level L. The formula that becomes false, I call it chi pi, and basically for the valuation v pi, and the level at which it occurs is L chi pi. So, having identified these, there are an infinite number of paths and every path has at least one such point. So, I collect all these L chi pi's into a set. It could be an infinite set, but the set is going to be finite. And why is it finite? Well, it follows from Koenig's lemma. Actually, it follows from a contrapositive of the Koenig's lemma. What does Koenig's? Here. Koenig's lemma says that every finitely branching infinite tree has an infinite path. If you take every finitely branching as an assumption, then every finitely branching tree which has no infinite path should be finite. Yeah, right. So, what am I saying now? How am I going to construct this finite tree? I have got this level L chi pi for each formula. Yeah. Okay. Now, I take this Herbrand tree of interpretation and chop it off at that point. So, that level L chi pi is a leaf node of that path. So, the entire subtree that comes below it, I chop it off. Okay. So, in every path there is one such point and I have chopped off everything below it, and I have got this finitely, it is still a finitely branching tree, but now by the contrapositive of Koenig's lemma, that tree cannot be infinite because there are no infinite paths. So, that entire tree must be finite, which means it has only a finite number of leaf nodes, which means that the set of formulae chi pi that I am collecting from the leaf nodes, that set must be finite. Right. One of the most ingenious proofs I have come across. Yeah. Right. So, now here is a finite set of formulae which does not have a model, which contradicts our assumption that every finite subset of theta has a model, and therefore, our original assumption that theta has no model is false. So, theta must have a model in the Herbrand tree of interpretations. right. Okay, but once we have proved this, then it is very simple. Compactness of first order logic is just that you take a set of closed formulae, sigma formulae, this set phi, by the way this set phi can be finite or infinite, closed now they are quantified formulae, right, has a model if and only if every finite subset of phi has a model. And what do? I just take each formula phi, again I go through the same kind of argument. I take each formula in phi and transform it into a Skolem normal form. But now I get SCO phi, which is in no sense no formula in SCO phi is equivalent to any formula in phi. But what I do know from Herbrand's theorem is that phi itself will have a model if and only if SCO phi has a model, and what I also know is that phi has a Herbrand model if and only if SCO phi has a Herbrand model, right. So, now what do? I concentrate on finding the Herbrand models of SCO phi, and now SCO phi basically it just consists of universal quantifiers and a body. That universal quantifier just means that I instantiate the body with all possible terms, and I apply the same reasoning that I applied here, right. So, it follows from the previous lemma that you will come to the same contradiction. Yeah. So, now your closed formula therefore will so what it means is that you will be able to show that so you will be able to show that there is a finite subset of phi which does not have a model, which contradicts your assumption, and therefore phi must have a model if every finite subset has a model, right. So, we have done compactness now, as well. It is a fairly ingenious proof, yeah, and after looking at the class, I think I should stop here. It has become heavy for quite a few. Right. Okay. So, what we do have to do more on first order logic before we get on to actually formal theories is completeness of pure predicate logic, undecidability of pure predicate logic. Once you have all these results, then you will not have unreasonable expectations about doing theorem proving and formal theories. Yeah. So, you will have only reasonable expectations. So, and then this all this will also lead into dovetail into essentially the domain of logic programming. So, this is a fundamental theorem. So, this Herbrand's theorem is a fundamental theorem for logic programming, right. Basically what it says is it saves me the trouble of trying to look for satisfaction of a set of formulae in arbitrary domains, and just look for satisfaction within the domain of terms itself, right. So, that logic programming therefore becomes possible within the notion of of terms and constructors, and you do not need to actually look at arbitrary theories, right. So, that is so these two are important. So, we have proved the compactness, and I think I will stop here now.